get started. Hopefully you had a nice weekend since we last met. I did a lot. Did the forces, battle the forces of Mother Nature, cleaned up leaves, and also washed and waxed my car for the winter, which is a good way to protect your paint, which is chemistry. All right, a couple things. I mentioned this, I believe, on Friday, but let me go through it again. This Wednesday will be test number 3. Test number 3 will cover gases and solutions. It has 9 pages, 20 problems. Some of the pages are multiple. Some of the problems are multiple part, and I believe there are 5 multiple choice. Points breakdown: 48 points gases, 57 solutions. That means, yes, there's 5 bonus points. And I've posted important information for test number 3 in the lecture folder of Blackboard. And that's information plus a periodic table you'll have on test number 3. Please be on time, please bring your calculator, and also writing implements, even though I'll have some extra erasers and pencils if you need it. Any questions on test 3? In keeping with all my tests, and you'll find out the final 2, that every question on test 3, I've covered the material or the concept behind that question at least twice, usually a lot more in class. What I'd like to do now, which I always do, is backed by popular demand to review for the next test. Everything you see on the slide here, A, you should know for test number 3, and B, it's available on Blackboard. And hold on one second. There we go. All right. Test number 3 starts out with gases. Remember, you're surrounded by a gas. Always, you're breathing it right now. And the first thing, when it comes to gases, you should know pressure. Pressure is measure of force per unit area, which I'll never ask on a test. But the units of pressure are, first of all, millimeters of mercury, mmHg, and torr. 1 millimeter mercury equals 1 torr. And also, there's a mistake on there which I corrected on the test, and I didn't do here, so make sure you correct it. That should be mm. And 760 millimeters of mercury equals 760, hold on. I know I corrected on the test, but there we go. 760 torr equals 760 millimeters of mercury equals 1 atmosphere. Those are a definition. Those are exact numbers. And also, when you're working with gases and the gas laws, you should know that you never use temperature in Celsius. It's always in Kelvin. And Kelvin is degrees C plus 273. 273 is also an exact number. And then there are key laws I asked you to learn, and we went through this. The first one, I'll never ask names, but I'll give this is all important information. I'll cover it in a second. And here, Boyle's law is P1 times V1 equals P2 times V2. where P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, and V2 is the final volume. And generally in problems, when we've done this in class, you're given P1, V1, and either P2 or V2, and you're asked to solve. And remember, anything divided by itself is the number one, and that's how you solve for that, which I went through these. Next one is my favorite mathematical equation in all of chemistry, and that is the ideal gas law, PV equal nRT. Now, P is pressure. It's always in atmospheres, but you're never given that in a problem in real life. It's always in either torr or millimeters of mercury, so you have to convert it. Volume is in liters. On my test, I'll always give you volume in liters. You won't have to convert it from milliliters. That's my gift to you. And next, N is the number of moles. And remember, moles are equal to the molecular weight of a compound is 1 mole. I don't have it here, but important information, I give that to you. I also give you this 1 mole equals the molecular weight of a compound, and the molecular weight of a compound is the sum of all atomic weights. T is in temperature, and it's in Kelvin, but I've never seen a thermometer that's in Kelvin. It's always in Celsius or centigrade. I use both terms, old school. But anyways, real old school. But you have to convert that using the K equals degree C plus 273 to Kelvin. And finally, R is the universal gas law constant, meaning it's always the same number. It's a constant. And for this class and everything I've ever used PV equal nRT, it's 0.0821 atmospheres, liters, mole K. Now, R is a calculated measured number. Therefore, the one I'm using right here has 3 significant figures. And before I forget, which I almost did, but let's start it around. And generally, you'll be asked to find something like P or V or N or T. Go look at the practice problems we've done. That will help you prepare. Common mistake, students don't convert. They leave pressure as millimeters of mercury or torr. You have to convert that. They use temperature as degree C. No, it has to be Kelvin. And instead of, you're always given weight, which you have to convert to moles, they use the weight. And those are common mistakes, and I'm telling you this so you know about it. Now, time out for commercial from Dr. White. If you missed last Wednesday, go look at YouTube. It's up and running, and it will help you prepare for test number 3. End of commercial. Oh, don't forget to send your money to the Save Dr. White Foundation, care of the local rock of the local train station. All right, let's continue. Oh, before we leave PV equal nRT, the other day when it got super cold and it was snowing, I was thinking, wow, I should keep an eye on my car tires, because your car tires contain gas, air, or if you want to spend money foolishly, nitrogen. They sell that at the dealerships. It doesn't make a big difference. And PV equal nRT tells you that when the temperature goes down, V, N, and R should stay constant, unless you got a flat and then all bets are off. But if you don't, when T goes down, pressure is going to go down. So in the winter, PV equal nRT tells you check your car tire pressure because it's going to go down. Now, the opposite of that is summer. I think I mentioned many years ago, what was it, 95? And I have to ask, how many of you can remember 1995? One or two, I can't. It was an interesting year. And if you drove around here that summer, we had a horrendous heat wave. The daytime temperature for almost 2 weeks stayed above 100 degrees Fahrenheit, which is quite hot. And it was actually, a lot of people died because of that. And if you looked around on the highways, you saw a lot of people with blowouts. Why? PV Glenn RT tells you that. Temperature goes up, pressure goes up in your tires. All right, let's continue. Next gas law I talked about was Dalton's law of partial pressures. And a partial pressure is the pressure of a gas in a mixture. If it were alone, that would be its pressure. We call that partial pressure. And Dalton's law of partial pressure, the total pressure of a mixture of gases is the sum of all the partial pressures. And again, we did problems with that. Now, because it falls into dealing with gases, I talked about boiling point. And boiling, danger, warning, time for Dr. Wade artwork. Look out. If you have a beaker of water, you can all laugh. This is a pretty good one of mine. I think I nailed it. But anyways, you have a beaker of water and you heat it up. This is a Bunsen burner, for those who don't know what it is. And what happens is you see these bubbles. And the bubbles are water vapor if you're boiling water. And vapor means it's this substance added as a gas. And they come up and collapse. And they give off their vapor. Now, when this happens, there's a pressure. And when the vapor pressure equals atmospheric pressure, when it equals atmospheric pressure, then what do you know? You measure temperature, and that's the definition of the boiling point. Now, an interesting fact you should know. The higher up you go in the altitude of our planet, the lower the atmospheric pressure, and because of that, the vapor pressure, the boiling point will be lower, because the vapor pressure, you need less energy to equal the atmospheric pressure, and therefore you will have a lower boiling point. So if you go to the top of the Himalayas, which I don't think I'll ever get to, but it's nice to dream about it. I'm not a mountain climber and never will be. But if you ever went up there and you were going to boil some water because you're at your campsite, you want some tea or noodles or whatever, and what happens to the boiling point of water? It's way lower than here in Glen Ellen. Why? Because the atmospheric pressure is much less, and therefore you need less energy, lower boiling point. And therefore, that's why I have that there. And that's something you should know. Same thing if you go to Denver, which is higher than Chicagoland here, lower atmospheric pressure, lower boiling point. All right, next I talked about solutions, and solutions are mixtures of two or more compounds that are totally dissolved, homogeneous, and they don't react with each other. None of the components lose their chemical identity. And when it comes to solutions, you should know there's a solvent. And we identify the solvent of the solution as the component present in the greatest amount. And all other components are called solutes. And if you thought about it, right now you're sitting in a solution, and what's the solvent you're sitting in right now? Nitrogen. Because nitrogen is 80 grams per 100 grams of air, and oxygen is only 20 grams per 100 grams of air, and therefore oxygen is a solute in the air we are. So solvent, component, present in the greatest amount, solute other components. Anybody think about solvents when you were in solutions, when you were driving here today? Anybody drive by a gas station and think about they sell solutions? We call that gasoline, which is a complex mixture. Anybody have any pop this weekend? Remember that soda, if you're from the Chicagoland area, we call that pop. And that's a solution. And what would be another one? Let's think of one more example. The tea I had this morning, that's also a solution. So those are solutions you should be familiar with. Now, something people mistake as a solution, but it's not, is a colloidal dispersion. In a colloidal dispersion, you have particles suspended in one compound suspended in another. They're not truly dissolved. And how can you tell that? Ooh. Time for Dr. White's famous demonstration. If you have a colloid, the particles are not totally dissolved. If you take a flashlight, which I just happen to have on my keychain, and you go through, see how the light goes through this? In a colloid, it wouldn't, because the particles scatter light. So an important way of defining or knowing if you have a colloid is, will it scatter light? And the answer is yes. How can you tell? Light won't go through it. And if I had tea in here instead of water, the light would go through, and that would tell you it's a solution. Now, what are examples of colloids? Well, are colloidal dispersions? No. Also, latex paint. Also, also after Halloween, but I can still say it, your blood. And those are important colloidal dispersions. I guess you could also say your ketchup, mustard are also colloidal dispersions because light don't go through that, and barbecue sauce, if you're into that. Now, next thing, and why it's not centered, the dreaded don't center it flavors got to me. Next thing I'd like to talk about is light dissolves light. Notice there's a subtle hint there. Know this, because I think it's one of the more important things you'll learn this semester that pertains to your daily life. And light dissolves light is light solutes are soluble in light solvents, and which means polar solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. And if you try to mix the two together, they are not soluble. And if you notice, I didn't put on there, one of these days I'll remember to do that, but this is something you should know. What are polar things? The most important polar thing is what's in this bottle, water. Next, salts like sodium chloride are polar, alcohol is polar, and sugar is polar. Now, what's nonpolar that you should know? Nonpolar, well, vegetable oil is nonpolar, gasoline is nonpolar, some products you use at home. Baby oil and Vaseline are also nonpolar. And if you've ever seen oil vinaigrette dressing, the oil is usually vegetable oil, olive oil, something like that, and the oil vinaigrette, vinegar is just mainly water, and that's why when you mix them together and you buy the bottle, you see two layers, because they're not soluble because of light dissolves light. everybody catches up. Now, when we talk about solutions, the important factor is solubility. And how much can you dissolve of this one substance in another? And we call that the solubility of a solid. And that's the maximum solute that will dissolve. If you try and put one more molecule in there, it won't dissolve because you're at the limit, period. All right. Now, when we talk about solutions, there are different types of solutions. One is saturated solution, and a saturated solution is a solution that contains the maximum amount of solute that can be dissolved under the conditions at which the solution exists, meaning mainly the temperature. And you can't put one more molecule, dissolve the solute in there, it will precipitate out, because you can't. Next, you have a dilute solution. And a dilute solution contains a small amount of solute relative to what could dissolve. By the way, bartenders don't like being told, did you dilute this drink? Meaning they didn't put a lot of alcohol in there. They don't like that. And the opposite of dilute is concentrated solution. And a concentrated solution is a solution that contains a large amount of solute relative to the amount that could dissolve. And finally, probably the most useful and widely used type of solution is aqueous solution. And I don't have it up there, so I better put it on the board. When you see bracket, AQ, closed bracket, that tells you you have an aqueous solution, and therefore the solvent is always water. Aqueous solution comes from aqua, the word water, in certain languages, which is telling you that the solvent is water. Now, when it comes to solutions, the important thing is concentration. And the concentration I'd like you to know is the most important measurement dealing with how much of a solute is in a solution is molarity. And molarity is abbreviated by capital M, and it's a ratio of number of moles per solute per liter. But 1 liter equals 1,000 milliliters, and therefore molarity is equal to moles of solute per 1,000 milliliters. The moles is a calculated number, the 1,000 is an exact number. And this is important and you should know it. I will give that to you on important information. And we did problems like that. And I put at the end, I have an extra, oh no, not done yet. When we talk about molarity, we talk about moles, and this is something you learned for test 2, but I'll give it to you on test 3. 1 mole of a compound equals its molecular weight. The molecular weight of a compound equals the sum. I have up there 1 mole of an element equals atomic weight. Can you keep a secret? I don't think on a test for number 3 I've ever used atomic weights. We have to use them. It's always compounds. So, it's a secret. And again, molarity, moles of solute per 1,000 milliliters. Now, a common problem which we worked through a couple on Friday, how many grams of HCl are needed to make 563 milliliters of a 2.00 capital M HCl solution? When you're going from milliliters to grams, this is a 2-step process. And the 2-step is, first step, you have to go from milliliters to moles, and the second step, you have to go from moles to grams. And therefore, this is 2-step. In fact, do I have to, oh, I do. Someone close the door. If I can hear it, you can hear it a lot better than I can. Trust me, I know that's true. Why don't you try this one? Question is, how many grams HCl are needed to make 651 milliliters of a 2.00 capital M HCl solution? Forget there are only a couple more weeks, shopping weeks till Thanksgiving. By the way, everybody know what the best part of the turkey is? The part that went off over the fence last. In Yiddish, we call that the puppet, the tail. And we always fight over that in our house, but we don't fight, we divvy it up equally. We used to fight when we were kids. That and the skin are the best parts of the turkey. Now you know I come from an Eastern European background, grandparents. All right, let's do this. First question you should be able to answer is, what are you being asked to find? And the answer is, how many grams of HCl? What are you given? Well, you're given milliliters. And you're given this number, 2.00 capital M. And as soon as you see capital M, you know its molarity, which what this really means is 2.00 moles of HCl per 1,000 milliliters. Now, there's no way I can go from milliliters to grams. There's no way. But you can do it in 2 steps. I hate new markers. And first we'll go from milliliters. We want to go from milliliters to, and this should be moles. And how do we do that? And that's moles of HCl. We use our good friend, our good buddy, unit analysis. I thought I wouldn't get that in today. I did. And whatever you're trying to go to goes on top. Whatever you're trying to get rid of goes there. Where do you get those numbers? From the molarity. Molarity, moles per 1,000 milliliters. And therefore I can put in here 2.00, 1,000, 3 exact number. Let me get my calculator up. And here's the number I get. And if you round that off to 3 significant figures, this is the number you get. And again, you can round it off at each step like I do, or wait until the end. I'll calculate it both ways on the test. And next, if we go back here, on the slide it says step number 2. What am I going to do? Go from moles to grams. And if you look at the top, it says 1 mole of a compound equals its molecular weight. What do we have? 1.30 moles of HCl. If I can convert it in one step, what am I trying to get to? Grams of HCl. I'll use unit analysis, and that tells me whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. Where do I get that number? 1 mole equals the molecular weight of HCl. Oh, I've got to figure that out, which is why this is 10 points. It's a lot of work. And what's the molecular weight of HCl? The sum of the atomic weights. Remember, when you're adding, you have the same number of significant figures past the decimal as the number you're adding that has the fewest. You only look to the right of the decimal. That's 2. This is 1. How do you round this off to 1 past the decimal? Keep the 5, drop the 1. So this is 36.5. And this is one exact number, 3. I'm in my wheelhouse again, my favorite 3. I tell you, most people my generation are comfortable with 3 significant figures because your slide rule would only do 3 significant. Oh, I hate to say it. That was before they had hand calculators. They had TV and crawlers. And if you notice, you get the same number each way. If you round either one of those off or both of them to 3 significant figures, and the answer would be 47.5 grams. And the important thing to remember is there's no way from going milliliters to grams, so you have to do it in 2 steps. First step, go from milliliter to mole. Second step, go from mole to gram, which you learned hopefully for test 2. If not, make sure you know it's test 3. Any questions before I erase this? Once, twice, 3 times. And why don't you try one more? Repetition is good for the grade. It helps you learn things. And I'll put up what's on. And that should give you everything you need to know. So have fun. I'll come back and go take a walk around the block. Oh, one thing I forgot to put up here. Atomic weight of oxygen is 16.0. give you one more, 30 seconds, 30 seconds. Get those fingers moving quick. Four, three, two, all right, put your pens down. Let's do it. All right. If you had problems with this, watch what I'm going to do. Also make sure you practice this for Wednesday. Now, what are we being asked to find? What's the volume? What are we given? Well, we're given a cylinder and it has 64.0 grams of oxygen. Oxygen is a gas. Hopefully you've learned that. And we're given a temperature and we're given a pressure. Now, if you look at this, you have a gas. Is anything changing? And the answer is no. Immediately that should tell you gas, nothing's changing. A lot of points. So PV equal nRT. We want to solve for volume. How do we get a load on one side? We divide both sides by pressure. Because anything divided by itself is the number 1. And now we have to get to work. Because if you look over there, which you'll be given, N is moles. We don't have to have that. We don't have it, but we can convert this into moles. R we're given, you will be. T is temperature in Kelvin. We've got to convert this. And P is pressure in atmospheres. We have to convert this. So let's find N, which is moles. And what we have is 64.0 grams of O2. We want to get the moles of oxygen. What do we do? Well, I didn't have it up there, but it's on. Sorry about this. It will be on important information, and that is somewhere here. How did I lose it? All right, let's do this. And test 3, this is important information. 1 mole of a compound equals its molecular weight. Molecular weight is the sum of atomic weights. So I have 2 oxygen, 2 times 16.0 equals 32.0. And now I know, using unit analysis, 1 mole of oxygen per 32.0 grams. And if I do my math, this is 2.00 if I did it correctly. I cheated. And next, what do I need? Well, R I'm given. Let's find out if I'm telling you the truth or not. If you look at important information, you're given this, so R I'm given, so I don't have to do that. Next, temperature, and temperature is in K, and K equals degrees C plus 273. And if you look on important information, I have it right here. And now I know that's 102 degrees C plus 273. add that up. If I did my math correctly, if not, someone please correct me. And last is P in atmospheres, but we're given it in torr. And how do we do that? Well, if we can convert it in one step, now use unit analysis again. What I'm trying to get to goes on top. What I'm trying to get rid of goes underneath. Where do I get that? I'll scroll back up a little under important information. And I got it right here on the test. This is the review, I got it fixed. And notice right here, 1 atmosphere, ATM, is 760 torr. These are both exact numbers because this is a definition. And therefore, now I can go to my calculator. Now, here's what I get for my pressure. I round that off to 3 significant figures. That'd be 1.12. And now let's do some math. And I have my moles times R times my temperature, and then I'll take that number and divide it by this, and I'll use this side too, do the same calculation. My goodness, I'm on a winning streak. Both ways work, but let's go through and put this in here. And here we got 1.12. And so now put in moles. 2.00 moles O2. R 0.0821 atmospheres, liters, moles, Kelvin. And next, I'll put in my temperature, 375 K, divided by the atmospheres, the pressure. Now, you might want at this point check that I set it up correctly. When you have this on top, first forget about the bottom, and what do? Notice moles divided by moles. Here I have Kelvin divided by Kelvin. That cancels out. Now all left on top is atmospheres, liters, divided by atmospheres. This cancels out. I'm left with liters. I'm on the right track. And therefore the answer here would be 55.0, rounding that off to 3 significant figures, liters. And that's how you do it. Any questions? And this is something you should know how to do, because PV equal nRT in my book is very important. Any questions on any material on test 3? All right. Don't forget to bring your calculator. Don't forget to bring your writing implements. Please be on time. And with that, let's continue with acids and bases. This will be on test 4, not test 3. Now, the question I started talking about last time was acids and bases. What's an acid? What's a base? And the first to come up with an answer to that, do not copy this down, was Arrhenius. And Arrhenius said acids are something that produce hydronium ion. Don't copy this down. Trust me, I'm a teacher. Does that work? Not really today. Must be Monday for you. Anyway, an Arrhenius base is something that makes hydroxide. Now, let's talk about some key acids you should know the structure of, and then we'll talk about how we know these are acids. First, a loaded question from Dr. White. How many found the review useful today? Raise your hand. How many would like me to do it for test 4? All right, I will. Don't twist my arm. I'll come back and do it for test 4 too. All right, now there's some key acids you should know the structure of. Hydrochloric acid. Is HCl. Hydrochloric acid, guess what? You have some on you right now, actually in you. The acid in your stomach that helps break down food is hydrochloric acid. Now I was thinking one of the wonders and miracles of life is we all have cells in our body that manufacture hydrochloric acid, which is one of the reasons why you need salt, sodium chloride. But that's hydrochloric acid. Another important acid is sulfuric acid, H2SO4. And on a test, I could ask H2SO4, is that an acid or base or salt? And the answer is it's an acid. And of all chemicals made in the United States, and I think even worldwide, this is the most widely manufactured chemical in the United States by pounds. Why? Because it's used in so many things. Where's one use? I think you're all familiar with a car battery. And in a car battery is sulfuric acid that helps make the battery give out electricity to start your car. Sulfuric acid and hydrochloric acid are very dangerous acids. Back when I was in high school, now for many years batteries are totally sealed. Back then they had caps you could take off and add some water. And one time I was helping my father change his car battery, and it was the winter, and I wasn't careful, and I tilted it. I got some sulfuric acid on my winter coat, and the stuff burned holes right through the coat. And that was the end of that coat. My mother, oh, was she mad? My father said, you should be more careful. I should have warned her. Well, I did, and I learned my lesson the hard way. And sulfuric acid is used for many things, to make many things in our daily life. Next one you should know is nitric acid. And nitric acid is also used to make many things. HNO3. And the last one, acetic acid. I'll draw the organic chemical structure. It's got 2 carbons, 3 hydrogen. This one I will never ask on tests as an acid or base, but I do want to talk about it. I will bet, and by the way, did I tell you I don't bet when I know I've won, that everyone, or I should say 99.5% of everybody in this room has acetic acid in your house. I don't have acetic acid. Yes, you do. If you take 4% approximately acetic acid and approximately 96% getting ahead of myself, water, you mix it together, you get a homogeneous solution, and we have a name for that solution. We call that vinegar. Any vinegar you have is essentially acetic acid and water. Certain vinegars have other flavorings in it. If you have, let's see, apple cider vinegar, it has different flavor than pure vinegar, which we call white vinegar. And also if you buy other things, you can get champagne vinegar. You can also buy different versions of Japanese vinegar, which is quite good. My favorite is Marucan Gold Label Japanese, which you can now get at most grocery stores. And these are all acids. Now bases, which I'll teach you in a little while, in Arrhenius it's something that gives off acid H+. Bases in water give hydroxide. And one of the key bases is sodium hydroxide. And the old name was lye. How many of you have ever heard of lye soap? Have you ever heard about it? Have you guys been? Anyways, that's soap made with sodium hydroxide. And another key base is potassium hydroxide. Now, I should tell you that if you go to a big box store like Home Depot, most of the drain cleaners are acid, usually sulfuric acid or hydrochloric. However, there's one that's a mixture of sodium hydroxide and potassium hydroxide. And it turns out that's the best drain cleaner they sell, and it's the only one that's made up of bases. Do I have time? I do. Let's go out into the real world. By the way, I don't get any kickbacks from Home Depot. I gotta find a way to get kickbacks from companies and products when I mention it. You know, like in the movies, buy new Ice Mountain water, and then they'll send me a check. No, that would be nice. All right. True story. When I moved into the house I own now, I've been there less than a month, and my kitchen sink stopped up. And obviously the previous owner or his wife dumped grease down the sink and it clogged it up. You should never put grease down the sink or any kind of oil because it will solidify. So I figured, all right, new house. I called the Roto-Rooter guy. He came out, Roto-Rooter. It was within a week and a half, it was clogged again. Well, he had a 6-month guarantee. I called him and said, hey, it's clogged, come and fix it again. And he did. Okay, thank you. And within a week and a half, 2 weeks, it's clogged again. Now I'm getting upset, not because of the money I spent to get it supposedly roto-rooted out, but the time I'm wasting waiting for this guy and not being at work. Being salaried at the time, I didn't lose any money, but it was still time I'd rather spend elsewhere. And he comes back, Oh, I apologize, he wrote a root, and then he takes out a bottle and says, I'm gonna put this good stuff in there. And I can see, can I see the bottle? I read the label, being an organic chemist, I saw essentially with soap in there and some surfactants, and that's gonna do nothing. And guess what? A week later, it's clogged, and I figure I'm through wasting my time with this guy. Forget about the money I spent, I'm wasting more of my time, which is more valuable to me. Back then, I was earning a six-figure salary, so it didn't bother me. But I went to my local Home Depot store, and I look at it, here's a wall, about the length of that wall there, almost, full of drain cleaners. And I'm looking at them, and one of the nice people who worked there comes up to me and, can I help you, sir? I said, sure. Of all these drain cleaners, which one do plumbers get? And immediately, without thinking, he pointed to that one. And he said, that's the one. And it was the only one in there that was a bottle in a thick plastic Ziploc bag. And on the bag it said, please use proper eye protection like safety goggles. Or it said, please use safety goggles when using that. So I pick up the bottle, and I'd already looked at the bottle of Drano and a couple others, which were HCl acid. And this was a mixture of sodium and potassium hydroxide. And then I learned a very important lesson in life, and that was, even with a PhD in synthetic organic chemistry, don't argue chemistry with a person who works at Home Depot. Because they said, oh, this is a base. He said, no, it's an acid. I said, no, it's got sodium hydroxide potassium. I'm a chemist, I got a PhD in it. It's a base. No, it's an acid. At that point, I realized, you know something, he helped me. Thank you, sir. And I just thanked him and went and bought the stuff, put it down my drain, followed the instructions, cleaned. About 10 years later, got clogged again, cleaned. This stuff works. Many of my students, I told the story, have used it. It works great in the bathroom too for hair clogging up, much better than the others. And so if you ever have a clogged drain and you forget, email me and I'll tell you this is stuff to buy. I keep a bottle this size in my house, and about every 7 to 10 years I have to clean out my drain in my kitchen, which is not too bad. And I do wear safety goggles, and I wear a long sleeve top or a lab coat just to be on the safe side. I've never had problems with this stuff works. And I don't think they sell it at Menards or Lowe's. I might be wrong. Another important base is ammonia. And ammonia is NH3. It's a gas at room temperature, but you're going to say, oh, I can go to my local supermarket and buy ammonia in a bottle. No, what you're really buying is a solution of ammonia in water, not ammonia. And one of my least favorite memories, I was at one chemical plant that I worked for that company, and I was supervising something, and we were almost done, and the plant manager came up to me and says, I'm short a manager, can you help me out? And I said, sure. What? And this is middle of summer, it's hot out, and he said, we're unloading a tank car, 250,000 pounds of ammonia, high pressure liquid ammonia. Could you supervise it? I thought, oh, all right, I'll help you out. You've been very nice to me always, so I figured I'd help him out. What that meant is, first of all, I have to get into a hazmat suit like you see in the movies and TV, and wear gloves and boots over my shoes, and then you duct tape it, and then on your back you have a pack of air, a bottle of air, and you have a gas mask. And if you're ever out in the summer wearing a gas mask, which I have been in a plant, and all of a sudden you start to sweat, you can't go like this and wipe it off, because if you do, you break the seal and you die. And so here I am, and it's getting into my eyes and going like this, and I just said, I'll just live with it. And we unloaded it because it's quite a hazardous job, and it's one of my more unpleasant memories of ammonia. And now, the last chemical I would like to talk about, that's a base, is sodium bicarbonate. And you know it as baking powder. And baking powder is the little can you buy. I don't know why they make it this size. I guess keeps costs down. And all my life it's been about this big. It's either a red one called Calmet, or if you look in the supermarket, they now have, Myers has theirs, Walmart has the store brand. And also if you look in certain supermarkets, there's this weird brand from Indiana called Gabler Girl. Don't ask me how they, well, you can look on their website to see how they got the name. But this is a weird name, Gabler Girl. Anyways, sodium bicarbonate, if you do any cooking, especially baking, you know that's an important chemical. Now, turns out the Arrhenius theory, which I told you don't copy down, doesn't work. Why doesn't it work? Well, you have to be in water. What if you're not in water? How do you know if you have an acid or base? Well, it turns out that's a major flaw or problem with that theory. And two chemists, Bronsted and Laurie, came up with their acid-base theory, which to this day is being used. And it explains what happens, I use the fancy word, non-aqueous, when you're not in water. And I will never ask you what's the advantage of using Bronsted and Laurie. But what is a Bronsted-Laurie acid? I do. I forgot something on that slide. Again, this is for test 4. Look at I'm being subtle. And a Bronsted-Laurie acid is any substance that can donate a proton. If I have a proton, which is abbreviated by H+, and I have, here, take my proton. I'm an acid, proton donor, H+. And all the beauty of the Bronsted-Laurie theory of acid bases, all the Arrhenius acids are also Bronsted-Laurie acids. And it turned out that wasn't an easy thing to do until they came up with their theory. That works. And so, Bronsted-Laurie acid, proton donor, H+. Remember, acid, H+ donor. And I always do this, if I'm an acid, here, take my proton. Now, the opposite of that is a Bronsted-Laurie base. And by the way, the hint is still good. And a Bronsted-Laurie base is any substance that can accept a proton from other substances, otherwise known as a proton acceptor. If I come up to you and say, give me your proton, I'm a base. Proton, H+. If I want it, I'm a base. If I want to give it to you, I'm an acid. And you should know this. And it turns out all the bases under Arrhenius are also bases under Bronsted-Laurie, which is a good thing, which is why their theory is so beneficial to chemistry. And therefore, proton donor, when we're talking about acids and bases, this is called a proton. And if I'm an acid, I donate my proton to you. Here, take my proton. I'm an acid. If I'm a base, give me your proton. I'm a base. And it turns out strong acids and strong bases, strong ones say, here, take your proton. Hold on, I got a whole 60 seconds. Oh, wait a second, you're all edgy and itchy to get out of here. All right, run away. I'll see you on Wednesday. Please be on time. I let you out a whole 42 seconds early.